Alright everybody, so we're in section 8.2 talking about area of a surface of revolution. So we're just going to start right off and look at some formulas that we're going to be using here. So given a positive function f with a continuous derivative, we define the surface area of the surface obtained by rotating the curve y equals f of x from a to b about the x-axis is given by the formula, we call it S equals the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. Okay, so you can notice some familiar pieces in here. So the 2 pi f of x, right? If you think about what that represents, if we're talking about something being rotated, right, we're looking at something circular. So this is providing us with 2 pi r, right, the circumference of that circle. And then this piece, right, if that looks familiar, that was our formula for arc length, right, in the previous section. So we're going to be using this. Now we can also write this in Leibniz notation, so just going to do that right down here. So here we can distinguish between a function of x and a function of y. So using the Leibniz notation for the function of x, we write this integral from a to b of 2 pi y, right, where y is a function of x, times the square root of 1 plus dy dx squared dx. And then for x being equal to a function of y, we have s is the integral from c to d, and those are the bounds on y, 2 pi x, again, because x is a function of y, times the square root of 1 plus dx dy, and derivative of x with respect to y, squared dy. So we've got our two different versions of this formula. And these can be written symbolically using the notation for arc length, because again, this second portion here, this is the definition of arc length. So we can rewrite these as s equals the integral of 2 pi y ds, or the integral of 2 pi x ds. And this is where ds is equal to just that piece that we're leaving off. But notationally, we can write it in this shorthand. So if you ever see it written with a ds, this is really what it's talking about. It's just taking that integral with respect to the arc length. Okay, so we can see on the next page here what we have happening in this scenario. So if we're rotating something about the, we'll do the y-axis first. So here's x, here's y. Right, we take our point, wherever it may be, that's the point x comma y. That's our sample point. And rotate that. Then the radius of this circle, that's going to be x. So the circumference is going to be 2 pi x. And then how much of that do we need? Well, for the rotation about the y-axis, we need it to be related to however long this arc length is, right? That tells us how much of it is actually being rotated. So our rotation is going to be s equals integral of 2 pi x ds. Okay, and then similarly, if we're rotating about the x-axis here, so we have our point x comma y. That point gets rotated. So this radius in here is y, right? That's the y value. So their circumference is 2 pi r, again, is 2 pi y. And then our rotation is going to be s equals the integral of 2 pi y ds. Okay, so this is really what's happening in this situation. So let's go ahead and look at an example. So the curve y equals the square root of 4 minus x squared from -1 to 1 is an arc of the circle with radius 2. Find the area of the surface obtained by rotating this arc about the x-axis. Okay, so let me just draw a little diagram here. So normally we would have, so let me go ahead and just make our circle here, and I'm going to be taking off some portions of this. So there's our circle, but we only want the arc of the curve on the top portion, right? That's the positive square root section, and we only want it from -1 to 1. So that's going to be from right here to right here, and everything else we're going to get rid of. That's the arc that it's talking about. So now this is getting rotated around the x-axis. Okay, so rotated about the x-axis. See if I can do this as smoothly as possible. That's not horrible. So something like that. Give it a little more of a smooth curve there. Okay, so we rotate that about the x-axis. And this is the solid that we are trying to find the area of, right? The surface area. So when we're looking for our surface area here, we need to get a derivative first of all. So this one, we already have y written in terms of x, so let's go ahead and just use that. So we have y as a function of x, so dy dx, take the derivative here, that's going to be 1 over 2 root 4 minus x squared times the derivative of the inside function, so that's times -2x. So that's -x over square root of 4 minus x squared. So that's our dy dx. So s is the integral, and we saw x is going right from here to here, so that's from -1 to 1 of 2 pi y, again because y is a function of x, times square root 1 plus dy dx squared dx. Okay, so now let's just sub in the pieces that we know. Integral for -1 to 1 of 2 pi times square root of 4 minus x squared times square root of 1 plus, let's see, that derivative squared. The negative squared becomes the positive. We have x squared over the square root squared, so that's just 4 minus x squared in the bottom there. And then dx. So now we need to play around with this a little bit in order to get it to a point where we can actually integrate. So what we're going to do is within this square root here, I'm going to go ahead and get a common denominator. So try to combine those two. So this is going to give us, let's see, so we still have 2 pi times square root of 4 minus x squared. When we get a common denominator, this is going to be, the 1 is going to become 4 minus x squared over 4 minus x squared. So that's 4 minus x squared plus x squared all over common denominator of 4 minus x squared. And then dx. So combine, so 2 pi square root 4 minus x squared. The numerator, minus x squared plus x squared, so we're just left with 4 over 4 minus x squared. So if we take the square root of the numerator, so let me get that 2 pi out of there. Oh, and this is dx, by the way. If I get the 2 pi out front, -1 to 1, square root 4 minus x squared, split up this square root, so square root of 4 is 2, over square root of 4 minus x squared dx, and then we get some great cancellation there. So all we have left is the integral, 2 pi times the integral from -1 to 1 of 2 dx. So take our antiderivative. We get 2 pi times 2x evaluated from -1 to 1. That's 2 pi times 2 minus -2, right? So that becomes plus 2. So 2 pi times 4. So we get 8 pi. And 8 pi would be the surface area of this solid over here that we were just looking at a little bit ago. So this one right here that we're rotating. Okay, so we get a whole bunch of circles, right, added up as we go all the way down here. That's going to give us our surface area of 8 pi. Alright, so let's look at one more example. So the arc of the parabola y equals x squared from 1, 1 to 2, 4 is rotated about the y-axis. Find the area of the resulting surface. So let's see what we have here. We've got our axes. 2, 1, 2, 3, 4, 1, 2. Alright, so the point 1, 1 and the point 2, 4. And the parabola that connects them. And we rotate like something like that. Maybe a little more spread than that. Okay. So this is the solid that we're trying to find the surface area of. Now this one, we actually have two solutions for this, depending on which variable you want to use. I'm going to use both, just so you can see that they are the same thing, but it would be up to your discretion to decide which one to use. The one that you might think of initially is we have y equals x squared, so we can write that as a function of x, right? And it's already kind of set up for that. So this is probably the one that we would do if we just had to pick one. So, but here's our first solution. So y equals x squared. So the derivative dy dx is just 2x. So our formula for s, right, that's 2 pi y oh, excuse me, sorry. We're using the 2 pi x on this one. 2 pi x ds. And then this is integral from 1 to 2 of 2 pi x times the square root of 1 plus the derivative squared. So that's 4x squared dx. And now at this point, it just becomes an exercise in integration. So to do this integral, we are going to use a u sub for this. So we're going to let u equal 1 plus 4x squared, and then du is going to be 8x dx. And I'll go ahead and convert the bounds as well. So when x is 1, using this substitution, we have 1 plus 4 times 1 squared, so that's 5. And when x is 2, our upper bound, we get 1 plus 4 times 4, so that's going to be 17. So for this one, we get the integral from 5 to 17 of, let's see, 2 pi x, but our du value over here, right, said that 1/8 du equals x dx. So we're going to divide by the 8. So this is just going to give us pi over 4, and then times the square root of u du. Take the antiderivative, so we get pi over 4 times 2/3 u to the 3/2, evaluated from 5 to 17. So that is going to be, right, 2 pi over 12, which is the same thing as just pi over 6, times 17, to the 3/2, minus 5 to the 3/2. And if we write that, so the book likes writing these as roots, so that's going to give us pi over 6. So pi over 6 times 17 root 17 minus 5 root 5. Okay, and that would be our surface area. Okay, so that would be probably the traditional way we'd think of doing it, right? Y is a function of x. So now let's just look at solution 2. So we're just going to do this one more time. This time in terms of y. So if y equals x squared, that means x is the square root of y. So dx dy is going to be 1 over 2 root y. So in terms of s, we have 2 pi x ds. Okay, so this is going to be the integral from 1 to 4, because again we're dealing in terms of the y values now. So of 2 pi root y times the square root of 1 plus the derivative squared, so that's 1 over 4y. And then the whole thing is dy. Alright, so now we need to play around with this a little bit so that we can integrate. So let me get the 2 pi out of there. Integral 1 to 4. I'm going to go ahead and multiply the square root of y into this square root. Okay, so I can bring it in because they're both square roots, and then I'm going to distribute it. So this is going to be the square root of y plus 1/4 dy. And now this is something that we can actually just integrate as is. So this is 2 pi times 2/3 y plus 1/4 to the 3/2 integrated from 1 to 4. So that's going to be 4 pi over 3 times 4 plus 1/4 is going to be 17/4 to the 3/2. And then 1 plus 1/4, that's going to be 5/4 to the 3/2. Which is 4 pi over 3. And it's going to be times 17 to the 3/2 over 8 minus 5 to the 3/2 over 8. Bring in that 8. That's going to leave us with just a pi over 6 times 17 root 17 minus 5 root 5, which is exactly what we got before. Okay, so there are times when either variable is going to allow you to compute that surface area.